So in this lecture, we're going to start talking about chapter 14, which will continue with a lot of the ideas that we first discussed in chapter 13 of equilibrium, but in the context of acids and bases. So to kick off this chapter, we're going to start with our first and simplest definition that we have for an acid or base. We'll discuss three over the course of this chapter. The simplest and narrowest definition is called an Arrhenius acid, and that is when we consider an acid to be something that produces H plus ions or hydronium ions when it's dissolved in solution. For instance, if you had something like hydrochloric acid and you put it in a solution, you would see it dissociate into H plus and Cl minus. Since it's creating H plus ions, we then can consider it an acid. Writing a definition or just an equation there, we have HA, aqueous, going to H plus and A minus. You see there that it's creating the H plus ions. Of course, we also have an Arrhenius base definition, and the Arrhenius base definition says that in order for it to be considered a base, it must produce hydroxide ions or OH minus ions when it's dissolved in solution. So for instance, when you take sodium hydroxide, you drop it into a solution or into water, what you're going to see is that it's going to create hydroxide ions, and so therefore we would consider a base under this definition. Similar to the first one, we can also write a definition or a reaction for that where we have MOH, which is M stands for some usually metal salt, and then it's going and creating hydroxide ions when it dissolves, as you see there. Now, one of the reasons that we're not going to use this a great deal, it's important that you know it, but it's not something that we're going to use a great deal, is because it's limited to aqueous solutions only, and we want a bit of a broader definition, and that's going to bring us to the Bronsted-Lowry definitions that we're going to use for most of the chapter. This is a bit more of a general definition. The Bronsted-Lowry acid is considered something that is just a proton donor, so an H plus donor. A Bronsted-Lowry base is considered something that is just a proton acceptor. If we look at a reaction where we have HA reacting with some base B, we can see that the HA is acting as a proton donor as it donates its proton to that base B, and in the product we see we have HB plus. Okay, so we can consider that on the left HA is an acid, and notice on the right hand side it has this pair, it's paired with a base, okay, because when you strip away the one acid, it now would prefer to pick up a proton, and that A minus is now considered its conjugate base. You'll hear that definition quite a few times this chapter. Now B is a base, and then when it reacts and moves to the right hand side by picking up that proton and becomes HB plus, it is now considered an acid or the conjugate acid of B, the base. So one thing that we will have to define a number of times are conjugate acid-base pairs. These are just the chemical species whose formulas differ by only one hydronium or H plus ion. Okay, so we see HA and A minus, and we say B and HB plus in the example above. If we take the look at this reaction, in which we're just looking at an acid dissociation equilibrium, we have HA reacting with water to produce hydronium ion plus this A minus. So let's take our time to go ahead and define what the acid base and the conjugate acid and conjugate base are in this particular pair. So HA, we should notice, is the acid. It has a proton that it can donate, and water can accept that proton. Now, if we look at that conjugate base, it is the A minus species. It's only separated by that one H plus, so we should expect that to be the conjugate base that we have. And likewise for water, H3O plus, or that hydronium ion, is its conjugate acid. Okay. We go now to a base dissociation equilibrium, then we want to do the same thing, and we see NH3 and H2O here. That NH3 molecule is capable of accepting a proton, and that water is capable of donating a proton. And so what we see here is that we would define NH3 as a base, H2O as an acid in this particular problem. And then if we look at what its conjugate acid is for the ammonia, the NH3, when it picks up that proton, the conjugate acid is now NH4+. When we donate the proton from H2O, it now has a conjugate base, which is hydroxide or OH-. So we're going to practice labeling the Bronsted-Lowry acids, writing a balanced equation here for this dissociation in water, and writing what's the conjugate acid, what's conjugate base in this case. So we're going to start with the first one, looking at sulfuric acid. And so it is reacting with water. I'll put our appropriate labels of saying sulfuric acid is aqueous, water is liquid, and then sulfuric acid in this case is going to be the acid, as you might have suspected. Water is going to serve as our base. When sulfuric acid donates that proton to water, water is going to become H3O+, and as sulfuric acid has lost that proton, it is now HSO4-. So whatever is the acid, we go ahead and look at its conjugate pair. In this case for H2SO4, the thing that's only different by one proton is the HSO4-. So that is its conjugate base. And for the water, we look at that, and it must be that its conjugate is H3O+. It's the only one that's separated by one proton. And so the base gives rise to the conjugate acid in this case. So now we go down to HSO4- reacting with water, and we're saying that HSO4- as prompted in the problem is an acid, and so it is donating a proton to water. That's going to yield H3O+ for water, and now the HSO4- is going to be left as SO42-. And so HSO4- on the left was the acid, and the SO42- on the right represents its conjugate base. Water was the base in this problem, and then it becomes H3O+, which is its conjugate acid. NH4+ is going to be the acid in the last problem, and so it's reacting with water again, and water is acting as the base yet again. After NH4 donates that proton, it becomes NH3, and after H2O accepts the proton, it becomes H3O+, and that's the conjugate acid. So hopefully you see sort of the theme there: acid, conjugate base, base, conjugate acid that we see. So this problem asks, what is the conjugate acid of each of the following bases? So if we're looking at bases and we're looking for the conjugate acid, then we just need to add a proton to find the conjugate acid of any of these species. So taking that first example, do we expect it to be carbonic acid H2CO3 or CO3 2- that is going to be the conjugate acid for this particular base? Hopefully you said that it's carbonic acid, as that's what we would have if we added a proton to HCO3-. Going to carbonate, we should expect adding a proton will give us HCO3-. That'll be our conjugate acid in that problem. Hydroxide, add a proton to that, we end up with water, and so that is the conjugate acid in that case. If we take the H2PO4- and we add a proton to that, we should expect to see phosphoric acid as the conjugate acid in that case. One of the things that we will see as a theme is that when acids and bases react, they typically like to react to form a weaker acid-base pair. So if you have strong acids or strong bases on one side, and then weak acids and weak bases on the other, the reaction tends to want to go towards the weaker side, whatever that might be. So this problem, we labeled the acid base on the left and the acid base on the right. And if we are looking at this, what we're typically saying, just as I mentioned earlier, is a stronger acid plus a stronger base typically is going to yield a weaker acid and a weaker base. And so the reaction in that case is going to want to go to the right. And like I said, it's always sort of trending towards that weaker side of the reaction. Um, what is a weak acid, though? A weak acid is something that only partially dissociates in water, and it's considered a weak electrolyte. So you can see there in the middle example there, um, there's only a partial dissociation. Most of the HA stays in its current form, but a few of them break up into form the hydronium ion and a little bit of A minus, but most of it stays intact, and that's what we consider a weak acid. Now, if we have a very weak acid, that's something that almost has no dissociation whatsoever. And so you can see that in the very bottom row there, that bottom example, there's really no HO3 plus or A minus shown. That is in contrast, of course, to a strong acid, which, of course, is going to dissociate completely in water and then is considered a strong electrolyte. So in that case, if you had 3 moles of the strong acid you put in water, you'd expect to get 3 moles of A minus and 3 moles of H3O plus because it's going to completely dissociate. If I put 3 moles of that weak acid in a solution, I don't expect to get much hydronium ion or A minus. I'm probably going to have very close to 3 moles, maybe 2.8, 2.7 moles of HA in solution afterwards. If we look at just this charts of acid strength and base strength, you'll see that the things that are in that strong acids have conjugate bases on the right-hand side in that other column. So hydrochloric has chloride on the right, and that strong acid yields a very weak base. And if we go back to the middle, then we have a weak acid like HF yields a weak base like F minus, and NH4 plus, a weak acid yields a weak base like NH3. And if we look at something that has a very weak acid, something like hydroxide or ammonia, then they have strong bases associated with like NH2 minus or O2 minus that are present. And so anything that has a strong acid is going to have a very weak conjugate base. Everything that is a very strong base is going to have a very weak conjugate acid. And that is a trend we expect to see at all times. So let's take a look at this problem for an example. And so it gives us a acid on the left, HX, and an acid on the right, HY. And you can see it's asking which one's the stronger acid, which one's the stronger base. And then it asks us later which one, if we mix them both, which reaction would be favorable. And so if we go ahead and look at this, we should enumerate all the things there. So we have 4HX, 2 hydroniums, and 2X minus on the left. And on the right, we have 2 HYs, 4 hydroniums, and 4 Y minuses. Okay. Keep in mind that hydronium is an equivalent way to express H plus. This is something that probably heard at some point in the first semester. And it's just because hydronium is basically, water plus that H plus. And in reality, that proton sort of bouncing around, it's always associated with some water in our solution. So it's okay to express it either way. You'll see it used interchangeably. Which is the stronger acid, HX or HY in this particular problem? Well, if we look at this, HY dissociates more than HX. If that is the case, if we get more dissociation for HY, then we expect that it's donating more protons. If it's donating more protons, then we can say that it is the stronger acid. So HY wins out on that case. So contrary to that, what is the stronger base? Well, X minus is holding on to protons more strongly as an alternative way to look at things. The X minus is holding on to more protons and it's staying the form of HX. So in that case, we can consider that X minus is a stronger base. If we go ahead and mix equal concentrations of the reactants and products, what do we expect for the reaction? Does it proceed to the right or will it proceed to the left? Well, we now know that that HX is our weaker acid, and we've already discussed that Y minus is our weaker base. So that puts on the right hand side a stronger acid and a stronger base. So which way do we expect the reaction to proceed? We should expect that it goes to the weaker side. So in this case, it's fairly simple. We expect it to go to the left. And so the reaction proceeds to the reactant side in this case, as it's written. If we look at this problem, this would be clicker question. If we have equal concentrations of reactants and products, which way do you expect it to proceed? So you might need to look at that table. You do need to sort of look at that from time to time, that chart that was shown a couple slides back, to figure out what weak acids and strong bases and things of that sort. So if we look up there, HF is a weak acid, Br minus is a weak base, and I already had labeled that F minus is a weak base, and HBr is a strong acid. So if you had to compare those, you probably would see that we have a weak and a strong on the right, and we have weak and weak on the left. Which is the side that's a little bit weaker? Well, I think you probably could see that it should be the reactant side that is a bit weaker here. If that is the case, then we expect the reaction to proceed to the left. And so in this case, we expect B to be the correct answer here. Another clicker question. If we took nitrous acid and it says we have a weak acid and it exists in a solution as a mixture of HNO2, H plus, NO2 minus, and it says which of the following statements is correct. So if HNO2 were to dissociate, you'd be left with NO2 minus, which is its conjugate base. So I shouldn't expect that NO2 minus is going to be a strong acid. And if it's a weak acid, we don't expect it to give rise to this strong base either in this case. And so there's additional evidence in that, because we said in this mixture it has all three present, right? And if it was a strong base, we should expect that it's picked up all the H's to create a bunch of hydroxide. And if all of them are present, that can't be the case. We can write that as the reaction there for a weak acid going to a weak base. If we look through all those examples, the only thing that we have there present is really NO2 minus is a weak acid. Doesn't make much sense for C because it has no proton to donate. NO2 minus is a weak base. That's the only one that's really suitable. So we arrive at D as our answer here. Another thing to consider is bond strength and how strong an acid we're going to get. We're going to look at one type of acids for this argument, just looking at binary acids, and those are composed of H plus some other non-metal. So that would include HCl, HBr, H2O, NH3. And notice H2O and NH3 have more than two things, or two atoms present, but binary just means two elements present, hydrogen and something else. And so H2O and NH3 still stand. And so, and I guess maybe NH4 plus would have been more appropriate than to put NH3 in this case. But if we're looking at a weaker bond, we expect that it's going to be a stronger acid, because we're looking to be acidic, to donate that proton. It has to cleave that bond that's present. And so we expect a weaker bond should yield a stronger acid. This is reaching a bit further back, but if you remember from first semester, we said that we have H plus with a small 1s orbital, and we have, say, let's take for instance iodine or iodide. If we look at that, it has a large p orbital. And remember, if we have good overlap with those orbitals, we can have a stronger bond. Something as diffuse and large as iodine's p orbital is not going to overlap much with that hydrogen orbital. And so you're going to get very little interaction. And so you expect that bond to be relatively weak. However, when we look at something like HF, it has a much smaller p orbital and it's able to interact much more strongly with that s orbital of the hydrogen. And that's going to yield a stronger bond. So one thing we expect is, as we're going from the left side, or if we're going to looking at the acid strength, we can also correlate that with the bond strength. And as that bond strength gets stronger, we expect the acid to be weaker. Another thing that can affect the bond strength is the bond polarity. And so just taking a couple of these binary acids being CH4, NH3, H2O, and HF, we see that if we go across the period, the electronegativity is going to increase. Now, the more the electronegativity increases, the better chances that we can steal that electron from the hydrogen. So if we're looking for fluorine, it wants to steal that electron from hydrogen, and that proton is going to float away, and the fluorine will be left with that extra electron and be F minus now. Because it is more polar than the rest of those bonds shown, we expect that that is going to become a more acidic species than the others shown, like CH4, which isn't very polar at all. And so we expect for binary acids the acidity to increase across the periodic table from left to right. Another class of acids is oxoacids. These have a general form of HNY, O subscript M. N and M are just integers. Y is going to be the non-metallic central atom that's present. And so if we look at some examples, carbonic acid would be one, and it's just given by the formula of H2CO3. Nitric acid would be another, in HNO3. And another would be hypochlorous acid with just HOCl. And what we tend to find here is that as the electronegativity of that central atom increases, going from carbonic to say something like HOCl, what we see is because of the increasing electronegativity, it's able to weaken that OH bond, which will increase the strength of the acid because it's easier to cleave off that H+. So if we increase the electronegativity of Y, or we increase the oxidation number of Y, as we'll discuss just here in a second with more detail, we can expect an increase in the acid strength. So more electronegative or higher oxidation number. So looking at that idea of more oxygens being present, what's going to occur is we're going to get a larger oxidation number on Y. So each oxygen that we're adding is just pulling and pulling away that electron density from that central atom. In turn, what that's going to do is weaken the OH bond, and that's going to increase the acidity, allowing that H+ to sort of be cleaved much easier and donated much easier than it would have otherwise. And you can see here with the hypochlorous, it only has a +1. You move to chlorous acid, it's +3, chloric is +5, and perchloric is +7. And in each case, the acid strength is going to increase. So another thing, when we look at the dissociation of water, one question that we can ask is water an acid or is it a base? Well, water's amphiprotic, and that means it can accept or it can donate a proton, and therefore it acts as an acid and a base, or I should say acts as an acid or a base. If we look at pure water, a really small fraction of that actually does dissociate. So even just in pure water, you have a little bit of hydronium ions and you have a little bit of hydroxide ions that are going to be released. And that should be given by this chemical equation. So I just split up the waters to make it maybe a little bit more clear. And so you end up with an H3O plus and an hydroxide. If we look to draw the chemical equilibrium for that, we would get the product of H3O plus times hydroxide. We could also write that as H plus times hydroxide, and that would also be perfectly valid. This is called the ion product constant for water. Okay. Another one of these subscripts, another equilibrium. There's so many we get in chemistry. This is a very small number, or very small. We should expect that this is tending towards the reactant side. As I said, the very small fraction of water is going to dissociate. So if that is the case, do we expect to have a value for this to be 10 to the 14, 1, or 10 to the minus 14? And I gave a little bit more away than I actually wanted to, but anyhow. Hopefully when you're looking at that, you expect it to be very small, as this should be favoring the reactants heavily. So 10 to the minus 14 is the one that sounds reasonable here. Well, how can we take this and actually figure out what the concentration of hydrogen or hydronium and hydroxide is in just a typical solution of water when we only have water present? So if we go ahead and do this, we need to just set up an ice diagram. So I put that same reaction down here, write my ice diagram. Notice I go ahead and I slash out everything under water. Why is that? Because it's a pure liquid. We don't include it in our equilibrium equation. If we started out with 0 of that, then we expect that to be the initial concentrations of hydronium and hydroxide. The changes should be a positive x for both of them. And so if we sum those two, we get x's for each one. Looking at Kw, setting it equal to 10 to the minus 14, we just end up with x squared equals 10 to the minus 14. Simplifying that down, x is going to be the square root of 10 to the minus 14, which will yield 10 to the minus 7 molar. So that is quite a small number. So the hydroxide concentration and the hydronium concentration for pure water is going to be 10 to the minus 7 molar, a very small concentration. So in pure water, we found it was 10 to the minus 7 molar. How many water molecules are dissociating in this case? If we, or I guess I asked, are many water molecules dissociating? And the answer obviously is no. There's not many that are dissociating, and it turns out only about 2 in each billion water molecules actually dissociates. 2 in each billion. That's not very much. Okay. What tends to happen in acidic or basic solution? So in acidic solution, what we should expect is that we're going to be dominated by hydronium or H+ ions. So the concentration of that is going to be greater than the hydroxide ions. In a basic solution, we expect the hydroxide ions to dominate and have more than the hydronium ions. And if we're looking at a neutral solution, we should expect that the hydronium and the hydroxide are roughly on the same level. So we define this Kw as being the product of the hydronium ions times the hydroxide ions equals 10 to the minus 14. This becomes important because for any solution, this is still maintained. If we're looking at an acidic solution, we're still going to be governed by this equilibrium, and so there's going to be very few hydroxides in a very acidic solution. And we can figure out what that number is by using just this formula to relate the two concentrations to one another. If we're looking for the hydronium concentration, we know the hydroxide. I can plug in the hydroxide's concentration over 10 to the minus 14 over the hydroxide concentration, and I can figure out what that hydronium concentration is. Or if I want the hydroxide concentration and I know the hydronium concentration, I can plug it into that formula and I can figure out what that concentration is. Let's look at an example here. So let's say we have a sample of lemon juice and it has a hydronium concentration of 2.5 times 10 to the minus 3 molar. And we want to figure out what the hydroxide concentration for this solution is. And then we want to determine, is it acidic or basic? So the hydroxide concentration is going to be given by 10 to the minus 14 over the concentration of hydronium ions, which is 2.5 times 10 to the minus 3 molar. And that's going to give us 4 times 10 to the minus 12 molar. And in this case, we can see that the hydronium concentration is greater than the hydroxide. And it's lemon juice. We should expect that it's an acid. And so it seems on par with what we would expect for a acidic solution. If we took seawater, the hydroxide concentration for this sample is 2 times 10 to the minus 6. So what's the hydronium concentration? And then is it acidic or basic? So we set it up in a similar fashion. The hydronium ion equals just the 10 to the minus 14 over the concentration of the hydroxide ion concentration, which is given by 2 times 10 to the minus 6. That gives us 5 times 10 to the minus 9 molar. And we can see that 5 times 10 to the minus 9 molar is smaller than the 2 times 10 to the minus 6. So this yields a basic solution. All right, well, we'll pick up with pH in the next section.